after a very long break, I'm going to be making videos again. Until now, I've made my videos focus mostly on Java as a language and on the intricacies of the language. But from now on, I'd like to focus more on concepts in general that can be applied in any programming language you choose. In my old videos, I went over arrays and array lists, and now I'm going to start by talking about stacks and queues. Stacks are a last in, first out data structure, which means exactly what it says on the tin. It works a bit like that stack of plates you might sometimes see on a buffet that's mounted on a spring. The point is, you can only access it from the top. You can think of it as a container with 3 sides, like this. I'm going to fill it up with some numbers, but it doesn't have to be numbers, it could be anything. There's pretty much only 2 operations you can do with a stack. One of them is adding a new item onto the stack, which we call pushing something onto the stack, or getting the top item off the stack, which we call popping it. Queues, on the other hand, are a first in, first out data structure, which is what you want if you're waiting in line to get coffee. Unlike a stack, which just has a top, a queue has a front and a back. The front is where you get the next person in line if you're the cashier, and the back is where you go if you want to join the queue. A queue can also do 2 operations, quite like the stack, adding one in and taking one out. But for a queue, they're called enqueue and dequeue, and they access different ends of the data structure. To implement these and represent them in the computer, it's quite easy for a stack. You just need to set some space aside to keep these items, and keep a pointer to the top, which you then move around. It's a bit more complicated for a queue, because if you keep it going for a while, it kind of crawls forward like a caterpillar. So you can't just set aside space for it, because if you keep using it long enough, it'll outgrow that space. There's a neat way of doing it using a circular array. A circular array doesn't actually look any different inside the computer. It's just a normal array, but you write the operations so that every time they go off the end of the array, they go back to the start. Every time you dequeue an element, you're taking it off of the front, so the front pointer moves back one, and you're decrementing the index. When you're adding something to the end, you're also decrementing the index of the back pointer, it turns out. So we can use the same operation for both, because they only ever risk going off the back end of the queue. Now, we could write an if statement that catches the pointer if it ever goes off the end and goes negative. Or we could do a little bit of mathematical magic to make it work. The math is more fun, so that's what I'm going to show you. You do your operation as usual, decrementing the pointer, but then you add the length of your array, and then you take all that and you take the remainder by the length of the array. Here, I'll show you. If I'm enqueuing something and it goes off the end of the array, then my original index for the back of the queue was 0. I'm enqueuing something, so I'm subtracting 1 from that, and then I'll add the length of the array, which here is 7, and take remainder by 7. So that gives me 6 take remainder by 7, which is 6, which is where we would want the back of the queue to now be. It's the exact same thing for the opposite operation, dequeue. So here's another quick example with a length of 9. Just in case you're not convinced yet, here's one last example. If you're somewhere in the middle of your array, adding the length and taking remainder by the length will cancel each other out, and then you're taking the remainder by the length of whatever the index of the pointer is, which is less than the length, which means that the remainder operation does nothing. If you've watched some of my older videos, or you're familiar with data structures like array lists, you might wonder why we bother with these in the first place. After all, everything that they can do, array lists can do. Why not just use them instead? Well, first off, if you try making an array list, it actually does a lot of really fancy stuff, and it's a lot more complicated to make than one of these, which also means that it can be slower because it's doing more work to do more complicated things. The properties of first in, first out, and last in, first out also turn out to be useful for algorithms and doing things like graph traversal, which I'm going to get to after I've told you about graphs and trees. That's it for now. Next, I'll be looking at some things like Big O and other data structures like binary trees and AVL trees.